Welcome class, myself Professor D.S. Rai, Professor Department of Civil Engineering BBD, ITM Lucknow. Today I am going to discuss a course KCE 064 Foundation Engineering. Today I will discuss lecture 40, Idealized Soil Interface Behavior Elastic Models. References that I have taken: Dr. B.C. Punamiya, Soil Mechanics and Foundation; V.N.S. Murthy, Soil Mechanics and Foundation Engineering; Alam Singh, Soil Mechanics and Foundation Engineering; Neptel, and some material have been taken from internet. Today the content that I will cover: idealized soil, foundation and interface behavior, elastic model of soil behavior. So, first we will come to the idealized soil. The mechanical response of naturally occurring soil can be influenced by a variety of factors, and these factors are shape of the soil, size and mechanical properties of individual soil particles. Second, configuration of soil structure. Third, intergranular stress and stress history of the soil particles. Fourth, presence of soil moisture, degree of saturation and soil permeability. So, these factors contribute to a stress strain phenomena which display non-linear, irreversible and time dependent characteristic. Because these all parameters influence the stress strain phenomena, so that will display a non-linear, irreversible and time dependent characteristic. And to soil mass exhibit an isotropic and non-homogeneous properties. This is the ideal conditions. In order to obtain the meaningful and reliable information for a practical problem of soil foundation interaction, it become necessary to idealize the behavior of soil by taking into account a specific aspect of behavior. The simplest type of idealized soil response assumed linear, this is the important, linear elastic behavior of supporting soil medium. Means a stress and a stress curve is constant, means a stress is proportional to a strain. It is recognized that the assumption of linearity and reversibility of deformation implicit in a linear elastic behavior are not always rigorously satisfied by the natural occurring soil mass. So, the linear elastic behavior considerably reduces the analytical rigor expended in the solution of particular boundary value problem and useful information to make many practical problem of soil mechanics and foundation engineering. Means in idealized soil should be have a linear elastic behavior. This is the important. This will solve variety of problem of soil mechanics and the foundation engineering. Now, reinforced soil or mechanically stabilized soil consists of soil that is strengthened by tensile element such as metal strip, geotextile or geogrid. The development of polymetric materials in the form of geosynthetics have brought a major change in geotechnical engineering. The beneficiary effect the soil reinforcement are derived from number 1, the increase the tensile strength of the soil. Second, the shear resistance developed from the friction at the soil reinforcement interfaces. So, there is an increase in application of geosynthetic in geotechnical structure such as foundation, embankment, retaining wall, etc. One part is the mechanical effect of vegetation, the cohesiveness of banks and bed materials and resistance to erosion governs the channel form. These are the different researchers who have done many works in this field. So, second is more resistance bank, cohesive vegetated soil tends to result in the channel with the lower width to the depth ratio than irradiable bank, that is a coarse textured, unvegetated and undercut. Third is bank failure and retreat occur due to flow related to toe slope erosion. And mass failure. The next is extreme bank failure can occur by several mechanisms including cultivator failure of undercut bank, toppling of the vertical arranged slab, rotational slumming and wedge failure. The type of failure reflects the presence and degree of bank undercutting by fluvial scour or other mechanism and the characteristic of the bank materials. Driving force for extreme bank instability are influenced by bank height and slope and the weight of the soil and its water content and surcharge imposed by any object on the bank top. So, these are the different researchers that they have done many works in this field. Now, the next is uplift capacity for the reinforced anchor plate. The symmetrical anchor plates are a foundation system that can resist the tensile load with the support of soil around which the anchor plate is embedded. So, and it is used by the soil structure as a structural member and primarily to resist the uplift loads and overturning moment and to ensure the structural stability. A wide variety of soil anchor system have been developed in order to satisfy the increase in the foundation to resist the uplift responses. The engineers have shown that the uplift response can be improved by grouping the systematic anchor plate, increasing the unit weight embedment ratio and the size of symmetric anchor plate. The use of geosynthetics has been found provides a possible solution in systematical anchor plate responses. Now, this is the now come to the interface behavior of the soil. So, the friction between earth and the reinforcement is essential phenomena in the reinforced soil. The traction force developed with the soil are being transmitted to the reinforcement by means of soil reinforcement interface friction. Due to this, soil reinforcement interaction, the composite mass behaves as if it is a poses in the direction of reinforcement. A cohesion proportional to the resistance of the reinforcement to tension. The mechanism of development of interface friction between the soil and reinforcement element is a complex phenomena and is not yet very well understood. So, in order to determine the coefficient of reinforcement interface friction, normally one of the following two sets is preferred, that are: number 1, test the direct shear box using soil and the reinforcing material known as sliding shear test, and the second is pull out test on the reinforcement buried either within an embankment of soil or within the reinforced soil wall. In sliding shear test, the soil movement is a minimum at the interface. So, it is very important. The soil movement is a very minimum at the interface, since the movement of soil is restrained by the reinforcement and increase with the distance away from it. Whereas, in case of pull out, the soil movement at the interface will be the maximum, and since soil resists the moment of reinforcement and reduces away from it, the above relative moment induce a near constant volume condition for pull out test and constant normal stress condition for the sliding shear test. This is a sliding test. Here the soil, this is the wood, this is the displacement. Once the force is applied, this is a normal load is applied on the soil system, and there is a some sliding force is applied. So, we can see here, this is the reinforcement we have. Here the displacement of the soil will be like this way. At the center, the displacement will be the maximum, and at the edge the displacement will be more or less nil. So, once we have provided a reinforcement here, then the displacement will be very much low. We can see by this diagram, this is the resisting zone where many reinforcing bar, this is the active zone, and the geometric position of Tm. This is tau dt by dt 1 by 2b. This is the another, this is the pull out resistance of loose sand. Sorry. Here we can see the reinforcing bar is deformed or displaced at the center. So, the sliding resistance for the dense sand, we can see here there is no any displacement in the reinforcing bar. The apparent friction coefficient F star often from pull out test should use in case of reinforced earth retaining wall, since at the time of friction failure of the reinforcement where the punching shear will occur causing reinforcement pull out. The value of coefficient friction mu, that is equal to tan delta obtained from the sliding shear test, can be used for designing the footing resisting on dense sand reinforced with the stiff reinforcement. Now, consider a model of soil response which exhibit a pure elastic characteristic, means stress is proportional to strain. An elastic material or an elastic media will deform under the application of external force system. Upon release of external forces, the material or media begins its original configuration, means try to attain its original shape. If the curve of unloading does not coincide with the loading curve, the material or medium exhibit an elastic property. In such media, energy is dissipated during the loading cycle. The attention is restricted to the models of soil behavior for which the relationship between the applied force and the resulting displacement are given by the linear functions. So, here we can see this is the Winkler's model, which is widely used, and this is the premium model for the idealized soil. So, we can see here this is the idealized model of soil media proposed by Winkler in 1867. Assume that the deflection of the soil media at any point on the surface is directly proportional to the stress Q applied at the point and independent of stress applied at other location, means Q x y will be equal to K W x y, where K is the term as the modulus of subgrade reaction with the unit stress per unit length. So, we can see here this is the x, this is the distance, and this is the force applied. So, once force is applied and there will be a deformation like this way, again when the load is removed from the body or soil mass, then the deflection will follow the same route as when the loading is applied. So, the Winkler's idealization of the soil media consists of a system of mutually independent spring element with the spring constant K. See here, his assumption is that the total mass is now sitting on a spring of a series of a spring having a spring constant K, but these all springs are acting individually. This is the soil media and the Winkler's model, the soil media is replaced by the spring having a constant K. So, the load is applied here and this is the foundation slab model as beam and the plate. So, this is the basic of the Winkler's model. The Winkler's idealization represents the soil media as a system of identical or mutually independent, closely spaced, discrete, linearly elastic spring. According to this idealization, deformation of foundation due to applied load confined to the loaded region only. This is the main thing of this Winkler's model. So, the figure shows the physical representation of the Winkler formula. The pressure deflection relationship at any point is given by the KW, where K is the modulus of subgrade reaction. Winkler assumed the foundation model to consist of closely spaced independent linear spring. In such a foundation is subject to partially distributed surface loading Q, a spring will not loaded a region affected beyond the loading region. So, this is the base of this Winkler's model, means the load will not affect away from the loading area. For such a situation, a actual foundation is observed to have the surface deformation as shown in this figure. Hence, by comparing the behavior of theoretical model and actual foundation, it can be seen that this model essentially suffers from a complete lack of continuity in the supporting media. The load deflection equation for this can be written as P or Q is equal to KW, as we have discussed earlier. According to this idealization, the formation of foundation due to applied is confined to loaded area region only. The number of study in the area of the soil structure interaction have been conducted on the basis of Winkler hypothesis for its simplicity, because it is a very simple. The fundamental problem with the use of this model is to determine the stiffness of elastic spring used to replace the soil below the foundation. So, this is the a number of study of the area of the soil structure interaction have been conducted. The problem becomes twofold, since the numerical value of this coefficient of subgrade reaction not only depends on the nature of the subgrade, but also the dimension of the loaded area as well. Since subgrade stiffness is the only parameter in the Winkler's model to analyze the physical behavior of subgrade, care must be taken to determine it numerically to use in a practical problem. The modulus of subgrade reaction or coefficient of subgrade reaction K is the ratio between the pressure P at any given point of the surface of contact and the settlement Y produced by the load at any point. So, this is the first model of elastic behavior of the soil. The second model is Flanagan-Bordioch model. This model is a modification of the Winkler's model. In this model requires continuity between individual spring elements in the Winkler's model by connecting them by a thin elastic membrane. We can see here, this is the thin elastic membrane are connected over the spring under the constant tension T. So, here the tension is applied to work together all the spring at the same time. So, this is the elastic member that has been used by Flanagan-Bordioch model. And this can be represented by P by KW, that is T delta square W for the rectangular and circular foundation, and KW minus T dt square W by dx square for the stiff foundation, where delta square is the Laplace operator del 2 by del x square plus del 2 by del y is equal to T is equal to tension force. So, this is the second model of elastic model of soil behavior. The next is Hetney models. This model suggests in the literature can be regarded as the fair compromise between two extreme approach. So, in this model the interaction among the discrete spring is accompanied by incorporating the elastic beam or elastic plate which undergoes the flexural deformation. What happened? In the model we have discussed earlier, one has each spring has a separate identity, means they are not dependent on the other's behavior, where then second a sheet of membrane is placed over it to work together. Here both are the extreme case. So, in this Hetney models, a beam or plate with the flexural rigidity D is placed over the spring. So, it has a capacity to go for the flexural deformation. In the earlier there is no flexural deformation. So, you can see here this is the spring and the beam and the plate with the flexural rigidity, and this is the rigid layer over which the spring are laid. Then the next model is Pasternak model. The Pasternak model is another model apart from we have discussed above. In this model, existence of shear interaction among the spring element is assumed, which is accomplished by connecting the end of a spring to a beam or plate, and that only undergo the transverse shear deformation. The load deflection relationship is obtained by considering the vertical equilibrium of the shear layer. So, see here, this is the shear layer or of shear modulus G. This is the spring, this is the rigidity. So, here there will be only deformation by the transverse shear deformation. Then the next model is Kerr model. In Kerr model, the shear layer is introduced by Winkler foundation and the spring constant above. Below this layer assumed to be the different as per this formulation. The following figure shows the physical representation of this mechanical model governing the differential Hatney foundation equation for this model can be expressed as follows. We can see here, this is the first layer and this is the second layer. So, this is the foundation, this is the shear layer having shear modulus G, and this is the rigid. So, we can say this is the K1 and this is the K2. So, it is a combination of above all three we have discussed already. So, these are the different models of soil behavior. Thank you very much. Thank you.